Okay, welcome. Before I even start, I will gather quick statistics. Do we have anyone who is only English speaking? Okay, then I will continue in English. And how many software developers do we have here? DevOps? Okay, and who is running a JVM application, running or managing a JVM application that needs to be responsive? Really? Like not even half? What about IntelliJ, Eclipse? You are not running those? Okay, let's start. So probably now some of you are asking yourself this question: why do we need yet another garbage collection algorithm? Because right now we have like 3 of them. Serial, which is the most effective per CPU cycle, parallel, which offers the best application throughput, and CMS, which is working concurrently with application threads. So what is wrong with all of those algorithms that we need yet another one? Like all of them were designed for small heap. Well, it's actually not really true. Like when Serial was designed, the computers had like 32 megabytes of RAM. So no one was even thinking about giving 1 gigabyte to heap. When Parallel was written, 128 megabytes, and when CMS, 512. So actually, CMS had a chance to be like a good algorithm that can handle big heap because it's working concurrently with application threads. So it's doing work in the background. But because it works in a way that is causing the fragmentation of old generation, instead of like good algorithm for big heap, we got something like a ticking bomb. Because once the old generation is defragmented, it will need to run a full garbage collection cycle to compact the old generation. And this is like a bomb because it can take seconds or even minutes when you have heap, let's say, bigger than 10 gigabytes. When you have heap like 64 or 128 gigabytes, then this will take minutes. So that's why we need another algorithm like G1 that was designed especially for heaps bigger than 6 gigabytes. And since the very beginning, it was designed in a way that it's supposed to be a replacement for CMS. But it's working so good that it exceeded the expectations, and it will actually become a new default in JDD 9. And one of the reasons for this is that this algorithm is the easiest to configure from all the garbage collection algorithms that we have. All you need to do is tell him what is your heap size, how many memory you can actually give to this collector, and the max pause time goal. And this max pause time goal is something completely new to garbage collection algorithms. Because now you have a way to tell your garbage collector to not stop your application for longer than, for example, 200 milliseconds. And this whole algorithm is designed around this idea, to not freeze your application. This makes him the best algorithm, the best garbage collection algorithm for applications that needs to be responsive, like your IntelliJ or Eclipse. You don't want it to freeze like for 30 seconds, right, when you are writing new class. So it sounds a little bit like marketing, but it's like everything comes with a price, the same with G1. It offers the worst application throughput. It's around 90%. Comparing to other algorithms, where they offer you like 97 or even 99 in case of parallel, G1 offers the worst application throughput because it's like 10% of time JVM is actually trying to clean the garbage from the heap instead of doing logic of your application. And let's think for a moment if this is really a problem. Like, is it a problem that it offers the worst application throughput? And it depends. If your application is like with user interface, maybe web server, maybe something with graphic interface, then it's supposed to be responsive. Also, very likely, your server is not yet utilizing your CPU in 100%. So it means that you still have some computing power. Then you can like exchange this computing power to make the garbage collection working with just short pauses, doing most of the stuff in the background, and make your application responsive all the time. So how actually does it work? Like, it also relies on a theory that most objects die young. So the memory is divided into young and old generations, and young generation is further divided into add-in and survivors. This is exactly the same like in other algorithms. The most similarities G1 have with CMS because it's working concurrently with application threads. It has some short stop the world phases, and the worst thing, fail-safe to full GC. In my opinion, this is the worst because this is the thing that actually made CMS a ticking bomb, so something that can explode. But in case of CMS, it was designed like this. It was designed, if you run it for a long time, it will explode. It will perform full GC. In G1, it's different because if you don't mess up with any configuration too much, if you don't break it, then it won't perform any full GC. So it will do it only in some extreme scenarios. What is completely new to garbage collection algorithms, the heap is divided further into regions. So add-in, survivor, or old generation, this is not like continuous space in memory. All of those generations consist of several regions, and because of this, G1 can be very flexible. It can adapt the size of each generation. If he needs more memory for old generation or for add-in, then it will basically assign more regions to add-in, and this gives him the flexibility. And because of this, it can adapt to, during the runtime, to the memory usage of your application. And because of this, this algorithm is the easiest to configure, because you don't need to investigate manually how many memory you will need in young generation or old generation. It will adapt during the runtime. It will target to have around 2,000 regions, and those regions will have size from 1 megabyte to 32 megabytes. It needs to be a power of 2, and you can adapt the size. You can like configure it manually to tell G1 to use region size defined by this flag. And this will be imported a few slides later. So now you know how the memory is divided. Let's take a look how actually the garbage are collected from the heap. G1 will perform 3 operations to collect the garbage. There will be like young collection, mixed collection, and concurrent marking. I will start with young collection because it's the easiest one. What will happen is G1 will stop your application. It will get all the young regions, and it will evacuate alive objects to a completely new region. After the evacuation, the young collection is done, and the previous regions are returned to a pool of empty memory. Let's see a marking phase. Marking phase mostly is done in the background. So your application is working when G1 is traversing your whole heap and analyzing and marking alive objects. And this marking phase will start when your heap is occupied in more than 45%. But you can adjust this value, and by adjusting it, you can like sacrifice more memory or more CPU to have better or lower application throughput. Once the marking phase is done, so all the objects were already marked, it will happen probably that some regions contains only garbage, no alive objects. And those regions will be returned to a pool of free memory in the end of the marking phase. And for every other region, the G1 will calculate how many garbage and how many alive objects we still do have in those regions. And if some regions have more garbage than 35%, so less than 65% of alive objects, they will be included for the next garbage collection. After marking phase is done, once the young generation is filled, so we have no more space in Eden, and G1 supposed to perform a young collection, it will realize that by marking phase, some regions were added to a collection set. So instead of doing young collection, it will perform a mixed collection. And it will get all regions from young generation and the regions from old generation that have mostly garbage. So this is where the name of algorithm comes from, garbage first. It will evacuate those objects to a new region, and now spot that not all the regions were evacuated. We still have some regions here. And those regions will be evacuated during another mixed collection cycle. Once all the regions are evacuated, the mixed collection will be stopped, and then we will again have young collections, and then again marking phase and mixed collections. Amount of the cycles will be by default 8. So it will collect all the regions from old generation after 8 cycles. You can change this with this flag, but it's something that I don't really recommend. G1 have a mechanism called heap waste %, and this is the second flag that you can use to either sacrifice the memory or CPU, and again, either boost your application throughput or lower it down. It means that when G1 spots that it can collect less than 10% of the memory, less than 10% of garbage, then it will stop and not do anything. So it will not waste your CPU. And maybe now some of you, if someone was like carefully watching what I'm saying, will notice that if G1 is actually evacuating objects from one region to another, it means that those objects will have completely new place in the memory. This means that if something is referencing them, we need to go and update those references, right? Because we changed the address of those objects in memory. And to do it in a performant way, G1 have a mechanism called remember sets. For each region that is further divided into cards, each region has his own remember set. And those remember sets are to track incoming references. So G1 is actually tracking who is referencing the objects from this particular region. So in this case, in region 2, we have a remember set, and region 2 have some objects that are referenced from objects by region 3 and from objects from region 1. So in this remember set, we'll have information that we have incoming reference from this region and incoming reference from this region. Region 1 and region 3 have no incoming references, so those remember sets will be empty. And those remember sets, each of them have his own update buffer. It means that when you are like allocating new memory and then changing the references, then here we have something like a post-write barrier before the information will be actually, before you will change the memory, there is a post-write barrier, and the information will be put into update buffers. Those remember sets can have like 3 different kinds of granularity. First is sparse. In this granularity level, we'll have information that something from this particular card is referencing objects in our region. So in this case, we'll have this first level of granularity, just 2 cards are referencing something. And this is the best granularity for performance, because we'll need to just traverse those 2 cards to perform the collection. The next level, which is fine, will replace the cards with a bitmap from whole region. So we'll have a bitmap and 1 bit for each card. So in this case, we'll have a bitmap with just 1 bit set, and we'll have here 1 second bitmap. And this is worse. This is not the best for the performance, because then we need to traverse whole bitmap. But the worst is the coarse granularity, because then we'll have a bitmap of not cards, but regions. So in this case, we'll have a bitmap with those 2 regions. In reality, it's around 2,000, so it's 2,000 elements, 2,000 bits that we need to check. Okay, who thinks that this was like very technical and hard to understand? Okay, not even half. Good, because now we'll look even deeper. We will analyze the log from G1, and the first thing that you think when I say log, you probably think, okay, let's visualize it somehow. And there are not many tools that can actually parse the log and visualize it on graphs. One is GC Viewer, but because G1 is still under the development, it means that the structure of the log is changing from one update to another. The same with behavior. Some things are working a little bit differently. And GC viewer can parse only part of the log, like it weren't very successful when I tried it, and only logs from some specific updates. So it's much better to use Sensum from jClarity, even though this is like, it's not a free tool, but it's working very nicely. It also provides you some recommendations, like what flags to enable, so he can give you a better information on what's going on, but also it will recommend you to remove or add some flags to boost the performance. Before you can visualize the log, you need to have the log, right? And to have the log that is meaningful, you need at least print GC details flag. Without this, there will be nothing interesting for you to analyze. And the print GC application stop time, this is the flag that I'm recommending to everyone who is not like garbage collection specialist. But if you want to spot, if you have any problems with garbage collection, if there is any place for optimization, that I recommend to enable this flag, then grab the log, and if you will have here in stop times something that is, let's say, bigger than 2 seconds, then you can definitely make it better with G1. And the log is quite big, because this is the single entry from garbage collection, so quite a lot of information. And I will cut it and explain. The first line, GC pause young initial mark, it means that we are doing the young collection. And here we are starting the threads. We have 4 values here, so it means that 4 threads are working on garbage collection. We do external root scanning, so we are scanning the root objects in Java. Those are like threads, local variables on stack, or static values. So if you have perfectly designed application where everything is a static singleton, then this will take a lot of time. Then we need to update the remembered sets, so profiles those buffers that I mentioned. After we updated them, we can actually scan the remembered sets, then we can evacuate the objects, and we can terminate the threads. And those threads are trying to be like good friends, so they're trying to help their buddies, and they will try this amount of time. In this case, there was nothing to help with, so they terminated after first attempt. So we have the GC worker end. And in the end, we'll have a summary of clearing card tables, choosing next collection set, so the regions that will be included in the next collection, reference processing. Here we are processing the soft, weak, and phantom references. If you have a lot of caches on weak or soft references, then this can take a significant amount of time, and we are releasing the previous collection sets. The summary of the amount of memory that was used and that will be used. So here we know that Eden had like almost 3 megabytes of RAM, right? After the collection, it's 0 bytes. This is the size of young generation. Here we have the survivors and the total statistics for Heap. And the times, for you, the most interesting is that one, the real, because this is the time for how long your application was actually stopped. Concurrent marking phase, so this is the thing that is working almost whole in the background. The concurrent root region scan, it's important to remember that when this start, before it finish, we cannot do any young collection. So our application is working, is allocating some objects, but it needs to finish very fast, because otherwise it needs to cancel, G1 needs to perform young collection, and then it will return to doing this concurrent region scan. After it's done, the concurrent mark is starting. So this is the moment where G1 is actually traversing whole heap and marking alive objects. In the meantime, we can have many young collections. After it's done, we have the remark phase and processing the references. We have the cleanup. During this phase, the regions that had only garbage are returned to a pool. And we have concurrent cleanup. So what is important to remember, especially now when G1 will become a new default in JDK 9. There are some flags that you should avoid and some specific approaches how we configure and tune our JVM. Like, I know that some people like to set a minimal heap size to something that is very small, I don't know, maybe 16 megabytes, but they know that application actually needs quite a lot of memory, so the maximum heap size, they say, I don't know, 32 gigabytes. And this is not very good when you have G1, because the region size is calculated based on the minimal heap size. So if we will set minimal heap size to something that is less than 2 gigabytes and very big maximum size, the region size will be calculated based on those 2 gigabytes, so it will have 1 megabyte size of the region. And in the beginning, we'll have 2,000 regions. But when our heaps grows, like in this extreme scenario, when it will grow to 128 gigabytes, then we will have 128,000 of regions. And this is not very effective, because then the granularity of remember sets will be the worst one, so the application throughput will suffer from this. Also, the region size this is very important thing when we have something that is called Mongoose allocations. Mongoose allocations are when we try to allocate objects that are bigger than half of the region size. And what is important here, that those regions are allocated directly into the old generation, not young. So there will be no tenoring. So it means that they won't be cleaned by young collections. And now, if you will have like a loop that is doing something that is allocating a lot of memory. So if someone is doing string concatenations on a string that is quite big, it means that you will allocate a lot of Mongoose objects directly in old generation. And to clean them, we need to actually run the concurrent marking phase. And this is working in background. It needs to traverse the whole heap. It takes time before those objects can be released. And in Jira, we had a situation where someone wrote a code that was concatenating on a comment, and someone posted a comment where he put like huge log file of 25 megabytes. And someone was concatenating it. So it means that he was allocating 25 megabytes in old generation as a Mongoose objects. And it turned out that before G1 even started doing concurrent marking phase, it ran out of memory. So we had a crash of JVM. So to avoid this, we can adapt the size of the region. And to even check if we have a problem with those Mongoose allocations, we can enable this flag, print adaptive size policy. And here it's saying more or less that I will start concurrent marking phase now because I saw that you are allocating some big objects, so Mongoose allocation here. And I will better start the concurrent marking phase now because otherwise I may run out of memory. Next thing is print region liveness info, but this will print you information about each Mongoose objects that you have. So here we have Mongoose start and continuous. In this case, that was like Mongoose objects that was as big as 7 regions. Yeah, then you will have this drawback that the granularity of remembered sets is in this coarse state, so the worst one. So it will actually consume more time, more CPU, so application throughput will be worse. So that's why you want to avoid this situation and have around 2,000 of regions. The worst thing you can do to G1 is to leave those flags. And many people actually have them like in servers or in configuration of IntelliJ or anything, because those were the flags that were recommended in all the previous algorithms. So let's say that you were using the parallel or serial collector, and now you will update Java on your local machine to JDK 9. It means it will start using G1. And if you don't remove those flags, this is the worst state for G1. I mentioned it before that G1 is adapting the sizes of generations depends on the need. And if you define any of those flags, it basically means that you know better what the size should be. So G1 will not try to adapt them. What is even worse, G1, when you provide any of those flags, G1 will completely ignore this max pause time goal. So it won't target 200 milliseconds anymore. And because of those sizes, what can happen is something that is called evacuation failure. And this is the worst thing that you can have. When you grab your logs and see that you have like 2-space overflow or full GCs, it means that probably you have one of those flags defined. And in this case, for just 12 gigabytes of heap, we have a pause like 5 seconds here. But it can be worse. Like this is from Jira log from a customer running Jira instance. And look here, it was 95 seconds to deal with a 2-space overflow error. So now imagine that you are running Jira, you try to create issue, and you need to wait 95 seconds because before the garbage collector finish cleaning garbage. So how to avoid those evacuation failures? First thing, remove those flags. Just define the heap size, and G1 will work very nice and not far from optimal application throughput that you can get. If you have some specific scenarios, those are, if you want to go lower than 200 milliseconds, then you have those 2 flags, and those flags are saying G1 that the new size needs to be at least 5% of the whole heap. And they had a scenario in LinkedIn where they wanted to go below. They wanted to achieve 100 milliseconds. And it was not possible because of this. The young generation was actually too big to fit into 100 milliseconds. When they lowered it up to 2%, then the young generation was small enough so the collector could actually fit into 100 milliseconds. If you don't have those flags but still have evacuation failures, you can make the concurrent phase faster. And with those flags, you can define how many threads, with the first flag, how many threads are being used to work during the stop the world phases. Those are usually the slow phases, but young collection is stop the world. So those are the amount of threads that will be cleaning young collection. And you have the concurrent GC threads. This is the amount of threads that will work on a concurrent marking phase. You can make it faster by increasing this value. Those are the algorithms how to calculate how many threads are running now. It's also very easy to get this information from a log, because I show you that you have like 4 values. It means that those are like 4 threads running. So it means that for this, we have 4 threads. Next thing you can do is to start concurrent marking phase earlier by defining this to something that is lower. But you need to be very careful when tweaking this value, because let's say you have 10 gigabytes of heap, but your application is constantly using 5 gigabytes. It means that after running full GC, it will still use 5 gigabytes. If you set this value to something lower, then G1 will try to start the marking phase, and then it will check, calculate the liveness info. It will realize, okay, I can't actually collect more garbage than 10%, so it will actually give up, and then it will start again and again and again, like in a loop. So be careful when tuning this value. Another and the last thing, okay, not the last one, but you can increase the reserved memory %. This is creating something that is called fake sealing. So G1 will think that this memory is not existing for him, and he will use it only in those extreme cases when the evacuation failure is supposed to happen. Then it will use this memory like a safe buffer. And this will be the last thing that you can do to help your garbage collector. Don't waste the memory. This is a heap dump from a quite small Jira instance, and Jira had like 87 megabytes of duplicated strings. Anyone of you maybe have an idea how to deal with duplicated strings in Java applications? Yes, you can do the intern. But the problem happens when you are using some external libraries, and then you don't have access to those strings that are being loaded. Well, you can try to do some magic with reflection, which is not really recommended. But now in JDK 8, since update 20, when you are using G1, you have this another option that you can enable on JVM to do the string duplication. And this is heap dump from the same Jira, and you can see that like 80 megabytes. In total, the whole heap was around 600 megabytes, so 80 megabytes was saved. These inspections, this is taken from your kit, so you can use your kit to take heap dump and run those inspections like duplicated strings. You can enable this flag to get the statistics, how the duplication is working. And during the runtime of this application, it saved almost 250 megabytes on all generation. Questions? Okay, thank you.